Good morning.
Good morning, sir.
Ain't out from last class, Fatma?
No, sir.
Tell me the last topic.
We did the first and the second law of the temperature.
Thermodynamics. Okay. We did refrigerator and heat pump.
No, we have to start that.
Okay. So the last was a statement of second law, that is Kelvin statement and Clausius statement. This was the last thing.
Yes, sir.
Okay. So next, refrigerator and heat pump. It consists of first a cabin, that is a region of interest for it, a working tool or compressor, and next surrounding in which excess heat is being ejected out. Similarly, in case of heat pump, it absorbs heat from surrounding at low temperature by adding work from compressor. It ejects heat into room to warm it. In first part, this is cabin or compartment of fridge, which is for refrigerator act as region of interest. Which is at some low temperature T2. So it absorbs Q2 amount of heat from this to cool it down. By adding work from compressor, it donate or eject out Q1 amount of heat into surrounding. So that refrigerator by this way manages to cool this particular cabin down. In second part, heat pump, this is surrounding. In winter season at low temperature T2. So it absorbs Q2 amount of heat from it. By adding work from compressor, it donates Q1 amount of heat into room, that is a region of interest for this case. To warm it up. Is it clear, Fatma?
Yes, sir.
So in first part, we can say for fridge, it absorbs heat from cabin to cool it down by adding work from compressor. It ejects heat into surrounding. But in case of heat pump, it absorbs heat from surrounding by adding work from compressor. It donates heat into room to warm it up. First, write it down, then I'm defining how to calculate its efficiency and working performance. Fatima, done?
Yes, sir.
Okay. Now, first for a refrigerator, what will be its efficiency of working or working performance? So it's working based on how much energy it has extracted from this particular cabin to the total amount of energy supplied to it in the form of work done from compressor by giving it electrical energy. So the ratio of these two terms will be termed as its working performance. So in case of fridge, working performance is heat extracted from cabin to the work done by compressor. So working performance of fridge is represented by alpha. Heat extracted from cabin is Q2 and work done is Q1 minus Q2. In terms of temperature, it will be T2 divided by T1 minus T2. In case of heat pump, working performance or its efficiency is how much this particular heat pump has donated heat into this particular room to warm it to the total amount of energy given to it in the form of electricity as work done by compressor. So the ratio of these two quantity for the case of heat pump will define you its efficiency or working performance. So working performance in this part is heat donated into room to warm it up divided by total amount of work done by compressor. So working performance is beta, heat donated is Q1 divided by work done Q1 minus Q2. In terms of temperature, it will be T1, T2. Fatma, any doubt?
No, sir.
No. So up to this part, we have three different engines. First one was heat engine, second is fridge, and third is heat pump. So if you have to relate the working ability or efficiency of these three terms, we can say beta is alpha plus 1, and which is equals to 1 by eta. This is the relation between its efficiency of all these three. Just write it down.
Done, sir.
Now, related to this part, there will be a theoretical question. What will happen to the temperature of room if door of fridge is kept open? Will the temperature of room will increase or decrease?
Increase.
Yes,
Will increase.
increase. Why?
Because the cold air coming from the fridge.
Yes.
Therefore, the temperature coming from the fridge.
Okay, temperature coming from fridge. Let me define you. Suppose you have a fridge and its door is kept open like this. So on opening this door, this cabin and this entire room will act as common system or same system. So it will absorb lesser amount of heat from this cabin. So you will say from room. So it will absorb Q2 amount of heat, and by adding work from compressor, it ejects larger amount of heat, that is Q1, into same room. So on each cycle, amount of work done by compressor will tend to increase the temperature of the surrounding. Hence, the temperature of room will increase. Is it clear?
Yes, sir.
If the door of fridge is kept open, then cabin, and room will act as same system. So it will absorb lesser heat and by adding work of compressor, it ejects large amount of heat into same room. Hence, temperature will increase. So the next question is, so it will be better to use this particular fridge as multi-purpose. In summer, keep this particular door closed and it will act as cooling agent. In winter, keep this particular door open and it will act as a room heater or heat pump. So then why we need of heat pump? So let me define you. Just see according to this efficiency, which is more efficient in these two parts, heat pump or fridge?
Heat pump.
Good. So you can say heat pump is more efficient as compared to refrigerator. So it will consume lesser amount of electricity as compared to fridge to do the same job. That's why it will be preferred to use heat pump instead of refrigerator to heating agent. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
So this is all about this entire thermodynamics. Any doubt up to this part from this entire chapter?
No, sir.
So let's start with new chapter, that is Kinetic Theory of Gas, which is quite related with thermodynamics. So next is Kinetic Theory of Gas. First is, in this chapter, there will be some property of ideal gas. Property of ideal gas. In last chapter, I defined you difference between real gas and ideal gas. Real gas is a gas in which there is some interaction between particles, so it will have potential energy, as well as due to thermal or temperature, they will have kinetic energy. But in ideal gas, there will be no interaction in between particles. So first is there is no interaction between particle of gas. Next, each particle will move with the same velocity along all different coordinate axes. So velocity of particle along each coordinate same. That is velocity along x-axis, y-axis, and z-axis. All will be same. So if you write it in vector form, it will be v equals to vx I cap, vy j cap, and vz k cap. Now taking the magnitude of this entire term, you'll get v bar root under vx squared, vy squared, and vz squared. So on squaring both sides, you may write v bar square equals to vx square, vy square, vz square, and since these all are equal, so we can write it as vx square. So vx square will be 1/3 of v bar square. From this part we can say. Fatma, any doubt?
No, sir.
Next is each particle will act as a rigid sphere and makes collision with wall of the container or with neighboring particle. It will be always elastic in nature. So each particle acts as a rigid sphere. They collide elastically with wall of container and with neighboring particle. They will have energy only due to temperature. Contain energy only due to temperature. That is thermal energy. Just write it down. Done?
Yes, sir.
Figure it out related to these different property.
No, sir.
Now, we have to first derive pressure exerted by gas. So first is pressure exerted by ideal gas. Suppose there is cubical vessel. This is x-axis, y-axis, and z-axis. A cubical vessel of side L. This particular vessel consisting of n number of gaseous particles of identical mass. Let's say at any instant a particle of mass m is going along this direction, hit on this particular wall and get reflected back at same velocity. Since this particular collision is elastic in nature, so there will be no change in its momentum or its velocity. Consider a cubical vessel having side L in which n gaseous particle each of mass m are in motion. So to find pressure, first we need force, and to define force, we must need momentum. So first, change in linear momentum during this collision. So it will be P final minus P initial. Initially, this particle is going along left direction, that is negative x-axis, and finally on collision with the wall of container, its motion is along positive x-axis. So final momentum will be m times of Vx, and initial momentum in this part is minus of m times Vx. So minus and minus will cancel out. So you'll get change in linear momentum as 2 times mvx. Is it clear?
Yes, sir.
Next, for this particular collision, how much time it has taken to move from one end to other end and get reflected back. So next, time taken for this collision is distance covered by the particle divided by speed in that direction. So this particle must have moved from this end to this and get reflected back again to this point. So total distance is 2L divided by its speed along that direction is Vx. So we have change in linear momentum and time taken. According to second law, Newton's second law, we can say rate of change of linear momentum is directly proportional to applied external force. So we can say force applied on wall of container will be change in linear momentum divided by time taken. Change in linear momentum we have 2 times mvx, and time taken we have 2 times L divided by Vx. 2 and 2 will cancel out, so it will become mvx squared divided by L. But this is force exerted by just one particle. If you have to calculate for n number of particles, just multiply it by n. So for n particle, total force exerted will be n times m into Vx squared divided by L. Fatma, is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Okay. So we have just calculated force exerted on the wall of container. Now, this particular wall of cubical vessel is in shape of square. So pressure exerted will be force per unit area on the wall of the container on which it is striking. So area of wall is side square. Pressure exerted on wall is equals to force by area. So force, we have a number of particles, each of mass m, Vx square divided by L, and area of wall is L square. So this term become L cube, which is nothing but volume. Number of particles, each of mass m, so it will become total mass by total volume times Vx square. This quantity is also called density, mass per unit volume. Vx square, I have written in left part, is nothing but 1 by 3 V bar square. So if you substitute these values, you will get pressure is equals to 1 by 3 rho V bar square, since Vx square is 1/3 V bar square. So this is the final expression. Pressure exerted by ideal gas on wall of container. Is it clear?
Yes, sir.
Just write it down.
Done, sir.
Written. Okay. Now in this part, this is pressure exerted by gas. This is density. And this particular term is also called mean square velocity. So let me define you a question related to this part. In a vessel, there an identical gaseous particle. If mass of each becomes half and their mean velocity becomes double, how will pressure exerted will change? Try to solve using the above expression. Fatma, any idea how to solve?
No, sir.
You have written up to this part?
Yes. Sir.
Okay. Since we have formula, pressure exerted by gas is 1 by 3. If you write density as total mass by total volume times V squared. So in this part, this quantity and this quantity get changed. So this is first condition. Let's say equation first. In second part, P dash, we have to calculate 1 by 3 remains same. Number of particle, volume remains same. Mass now becomes m by 2. And velocity becomes 2 times v squared. Now just simplify it. You will get 1 by 3 n by v m by 2 as it is, and 2v on squaring, it will become 4v bar square. This term and this term will cancel out in 2 times. So you're left with 2 times 1 by 3 nm by v and v bar square. Let's say this is equation 2. Now just divide these two equation. So on dividing equation first and equation second, it will be P divided by P dash 1 by 3 nm divided by volume V bar square whole divided by 2 times 1 by 3 nm by volume V bar square. This part and this part will cancel out. So you'll get just 1 by 2. So on cross multiplication, P dash will be twice of P. Is it clear?
Yes, sir.
So related to this part, question will be only like this. Number of particle becomes 1/3, mass becomes twice, and velocity becomes half. These different problems will be asked related to this part. Okay, so just use the formula, write the given condition, and just divide them with the actual part. You'll get your answer. Just write it down.
Done, sir.
Okay. Next thing we have to calculate kinetic interpretation of temperature, or simply thermal kinetic energy. As pressure exerted by gas is 1 by 3 rho v squared. So we may write 1 by 3 density is mass divided by volume v squared. So move these two terms towards left side. So you will get 3 times P into V equals to m times V squared. Fatma, just tell me the formula of kinetic energy. Simply, what do you mean by kinetic energy?
1 by 2 mv square.
Good. So in this part, we have mass times velocity square, but we have to calculate it 1 by 2 mv square. So just multiply half to both sides, so that this entire term will become kinetic energy equals to 3 by 2 times PV. Is it clear?
Yes, sir.
So we have kinetic energy is equals to 3 by 2 P into V. So from this part, you will be asked, show that kinetic energy per unit volume will be 3 by 2 times P. So you may write kinetic energy divided by volume is equals to 3 by 2 times P from this part. Next, if you convert this PV according to ideal gas equation, PV is equals to nRT. So it will become 3 by 2 nRT is equals to kinetic energy. In this part, N is number of moles. So you may write number of mole as number of particle divided by Avogadro number times R into T is equals to kinetic energy. Now move this N towards left side. So you'll get kinetic energy divided by number of particle is equals to 3 by 2. Next is R by Na multiplied by T. This quantity is also called Kb, that is Boltzmann constant. So it will become first write it down, then I'm defining the left part.
Done, sir.
Now related to this part, kinetic energy by number of particles. We have kinetic energy divided by number of particles is equals to 3 by 2 R by Na multiplied by D. This quantity is called Boltzmann constant. This quantity is called kinetic energy by number of particles, which is also called average kinetic energy. So this is average kinetic energy, 3 by 2, and this is another constant Kb multiplied by D. So this is final expression of average thermal kinetic energy. In this part, Kb is equals to R by Na. Kb is called Boltzmann constant. R is universal gas constant, which is 8.314. The Avogadro number 6.022 into 10 to the power 23. So if you simplify it, you'll get 1.38 into 10 to the power minus 23 joule per Kelvin equals to Boltzmann constant. Fatma, any doubt?
No.
Now, from this part, we can say 3 by 2 and Kb is constant. So this particular kinetic energy is just depending on temperature only. So from this part, we can define absolute zero. You must have learned about it in your chemistry as well. Do you know what do you mean by absolute zero or 0 Kelvin? If you substitute the value of T to be 0 Kelvin, temperature is 0 Kelvin in this part. So you'll get average thermal kinetic energy is 0. If kinetic energy of particle becomes 0, it means there will be no randomness of particle. So we can say the temperature at which randomness of gas get stopped is called absolute zero or 0 Kelvin. And you can say it is the temperature at which there will be no existence of matter. Is it clear?
Yes, sir.
Just write it down.
Done, sir.
Okay. In this part, we have calculated average thermal kinetic energy due to monoatomic gaseous particle. But suppose if you have to calculate for any different gases, so let me define you how to calculate. So for that part, first, what is law of equipartition of energy? Equipartition, it means equal distribution or equal division of what? Energy. So we can say the total energy of gas get equally distributed along its all degree of freedom. Like we have for monoatomic, total energy contained is 3/2 kBT. How many degree of freedom are there in monoatomic gas? Fatma, tell me the number of degree of freedom for monoatomic gas.
3.
Good. So we can say average kinetic energy of monoatomic gas is 3/2 kBT. So in this part, we have 3 different degree of freedom. So this entire energy may get distributed along 3 degree of freedom equally. So along any one direction, it will be half kBT, half kBT, and half kBT. Is it clear?
Yes, sir.
So from this, we can say the total energy of gas get equally distributed along its all degree of freedom. And at constant temperature, energy in any 1 degree of freedom is equals to half kBT, and it is constant. Fatma, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Just 2 minutes. Okay, so we have along any 1 degree of freedom, half kBT energy. So if you have to calculate total energy contained in a gas having F number of degree of freedom. So total internal energy will be equals to F degree of freedom. Along each degree of freedom, we have half kBT energy. But this is only for one particle. If you have to calculate for n number of particles of gas, so according to the formula, number of moles is equals to number of particles divided by Avogadro number. So for n particle, it will be n times Na. Just put it, so it will become n times Na. If you simplify it, you will get half number of moles into F Kb into Na multiplied by T. This quantity is also called R, that is universal gas constant. So it will become half NF times R into T is equals to U. This is total internal energy for n number of particle gas. Is it clear?
Yes, sir.
So from this part, if you have to calculate CV, that is molar specific heat at constant volume. So molar specific heat, constant volume. According to the formula, CV is equals to 1 by N times del U by del T. That is differentiation of this particular function with respect to temperature divided by N. So N and N will cancel out and differentiation of temperature will be 1. So you'll get half F into R. Now, according to Meier's relation for molar specific heat at constant pressure, Cp is equals to Cv plus R. So Cv we have half times F into R. So you may write 1 plus F by 2 multiplied by R is equals to Cv. Is it clear?
Yes, sir.
Okay. So from this part further, we have to calculate value of gamma, that is specific gas ratio. Gamma is nothing but a ratio of these two terms. So specific gas ratio is Cp divided by Cv. Cp we have 1 plus F by 2 times of R, and Cv we have half of F into R. So if you divide these two terms, you will get 1 plus 2 by F. That's why I've written gamma equals to 1 plus 2 by F in thermodynamics. This is how we can derive from this particular relation. Any doubt, Fatma?
No, sir.
Okay, just write it down.
Done, sir.
Okay, related to this part, you will be asked if 4 gram of hydrogen gas is at 1 to 7 degrees Celsius. Find first number of moles, second total number of degree of freedom, third kinetic energy due to its translational motion, fourth kinetic energy due to its rotational motion, and fifth total internal energy. Let me define you how to solve. First, we have to calculate number of moles. We have given mass of hydrogen gas, that is 4 gram. So, according to the formula, number of moles is equals to given mass by molar mass. How much mass we have given? 4 gram. Molecular mass of hydrogen gas is? Fatma, tell me the molecular mass of hydrogen gas. Fatma,
Yes, sir.
tell me the molecular mass of hydrogen gas. Since hydrogen being gas, so it will act as H2 molecule. So its mass will be 2. So 4 divided by 2 will be just 2. So number of moles is 2. Is it clear?
Yes, sir.
Next, we have to calculate total degree of freedom. Since hydrogen gas is diatomic, so how many degree of freedom it will have?
5.
Good. So in one molecule, it will have 5 degree of freedom. So just multiply it by number of particles it have. So 5, number of particle is number of moles multiplied by Avogadro number. So it will become 5, number of moles we have 2, and Avogadro number is 6.022 into 10 raised to 23. So if you simplify it, you'll get 10. So it will become 6.022 into 10 to the power 24 total degree of freedom in this entire hydrogen molecule. Is it clear?
Yes, sir.
In third part, we have to calculate kinetic energy due to translational motion. In hydrogen molecule, it will have 3 translational degree of freedom and 2 rotational degree of freedom. So according to the formula of internal energy, we may divide it as half number of degree of freedom along its translational part multiplied by number of moles into R into T. So if you simplify it, you'll get half number of degree of freedom along its translational motion is 3. Number of moles we have 2. R is universal gas constant, so it will be 8.314, and temperature 120 degrees Celsius, 27 degrees Celsius. If we convert it into Kelvin, it will become 400. Just simplify it, you'll get your answer. So 2 and 2 will cancel out. 4 into 3, 1200 multiplied by 8.314. 1 minute. 100. It will become 997.6. That is 9.977 into 10 to the power 3 joule. Fatma, any doubt?
No, sir.
Similarly, if you have to calculate rotational energy, so kinetic energy due to rotational part, it will be half number of degree of freedom along its rotational, number of moles R into T. So it will be half number of degree of freedom due to its rotational is 2, number of mole is 2, universal gas constant 8.314 multiplied by 400. So 2 and 2 will cancel out. 2 into 4, 8. So it will become 800 multiplied by 8.314. So it will be 6.651. 10 to the power 3 joule. Now at last, to get total internal energy is nothing but kinetic energy due to translational part and kinetic energy due to rotational part. Just add them. So finally, you will get this will be your final answer. Any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Okay. So let's stop here for today. We have just finished half of this particular entire chapter, that is kinetic theory of gas. In next class, we'll start with mean free path and the rest of this particular entire chapter. Okay?
Okay, sir.
Okay then. Thank you.